Hi folks, in this video I wanted to quickly recap the consumer's utility maximization problem with a CES utility function. So I'm going to go right ahead and write out the consumer's Lagrangian. So we start with the Lagrangian is equal to the utility function, which is a sum over capital G many goods. And slightly differently from what we did in the tutorial, I'm going to have this alpha G parameter here, and I'll explain what that is. So this is the utility function. It's a CES utility function. The alpha G's are essentially, they affect the shares, the consumption shares of each good. And to complete the Lagrangian, we have our Lagrange multiplier and our budget constraint here. Okay, so let's take the first order condition with respect to xig. Now this section in the brackets here I'm going to define that as A. That's going to make the it's going to be just simpler to write, and it's going to be quicker, and it's also going to help me do the differentiation slightly easier. So I'm going to differentiate this A to the power of sigma over sigma minus 1. Now I'm going to differentiate the inner function with respect to xig. So the alpha g is just treated as a constant here. And xig, sigma minus 1 over sigma minus 1 is just to the minus 1 over sigma power. And then on the right-hand side, I have lambda I times pg, and all that is equal to 0. So we can simplify a lot here. Firstly, I can cancel these constant terms. I can simplify some of the exponents, and I can move the lambda I pg over to the right-hand side. So let me do that now. So that gives me a to the power 1 over sigma minus 1 times alpha g to the 1 over sigma times xig to the minus 1 over sigma equals lambda I pg. Okay, so this is a first order condition for good G. But of course I have G many first order conditions, capital G many first order conditions, with respect to every good. So the first thing I can do is divide the first order condition for one good with respect to by another good. So I can take the first order condition for G and divide it by the first order condition for good K. What does that give me? So let me just rewrite this again. Equals lambda I pg. And now we're dividing this on both sides. On the left-hand side by the marginal utility of good K. So I made a mistake there. This should obviously be the, this should say alpha K. And again here we can do a lot of simplification. So the A term on the left-hand side cancels, and the lambda I term on the right-hand side cancels. And we get alpha G to the 1 over sigma was xig to the minus 1 over sigma divided by alpha K to the 1 over sigma times xik to the minus 1 over sigma equals pg over pk. So the first thing to note is that this is the marginal rate of substitution between goods G and K, i.e. the ratio of the marginal utilities. And that is equal to, of course, the ratio of the prices, which, so that's the first condition for efficiency satisfied here. We have the marginal rate of substitution equal to the ratio of the prices. Graphically, this just looks like this. So the marginal rate of substitution is just equal to the slope of the indifference curve, and the ratio of the prices, well, I suppose it's the negative of the ratio of the prices, is the budget line. So this point here, where these two things are tangent, is what is described by this equation here. This equation describes the point at which the slope of the indifference curve is equal to the slope of the budget line. In other words, the marginal rate of substitution equals the ratio of the prices. Okay. I can rearrange this expression a little bit to get xig over xik, and that is equal to alpha g over alpha k times pg over pk to the power of minus sigma. So this is relative demand, the demand for good G relative to good K, and it's a function of the relative price of good G relative to good K, clearly. We can look at the elasticity of substitution, which, if you remember, the elasticity is a percentage change in demand relative to a percentage change in price. But here we're looking at relative demand, so it's going to be a percentage change in the relative demand, xig over xik, with respect to a change in the relative price. So in other words, the elasticity of substitution is going to be the derivative of xig over xik with respect to the relative price, pg over pk. And because it's an elasticity, we need to take the percentage change, so multiply by pg over pk and divide by relative demand xig divided by xik. Now, of course, you probably remember that the elasticity can also be written as the derivative of the log of, in this case, relative demand with respect to the log of prices. So the derivative of log xig over xik with respect to the log of pg over pk. And that's a very easy thing to calculate. We can do that very simply, take logs of both sides. So the log of xig over xik is just equal to the log of this constant term minus, using the properties of logs to bring down the power, log pg over pk. Okay, and if we differentiate the log of xig over xik with respect to the log of pg over pk, what do we get? Of course, we get minus sigma. So this tells us that the elasticity of substitution between good G and good K is just equal to minus sigma. So it's constant. And this makes a lot of sense. It's called a constant elasticity of substitution utility function. And of course, we therefore have constant elasticity of substitution. And the elasticity is just equal to this minus sigma.